Hi, in this video I'm going to go over Lewis structures. Lewis structures are a way to draw a molecule, and they're great because they can help you figure out what the shape of the molecule more or less is, and also they can help you figure out some of the behavior, predict how the molecule might behave or react with other molecules. I originally made this video during COVID when I was new to making videos, new to using drawing on a video, so you'll notice some glitches. But the basic idea is clear and straightforward. I have a couple tricks I wanted to share with you about Lewis structures. The video itself is pretty funny because it's the first time I've used my iPad as a drawing pad, and therefore you get a great view of the top of my head for most of this video. But 5 steps, 2 tricks. I'll put some links in Canvas to some more videos that are very helpful. I hope this helps. So let's start with a very basic Lewis structures, just so I can go through the 5 steps, and then I'll show you a more complicated one. So here we go. Let's just do the simple CH4. Okay, so step 1 is to count the valence electrons. So step 1, count the valence electrons. The valence electrons are electrons from the outermost shell of each atom that are the ones involved in bonding in the molecule. C has 4 valence electrons. You can see that when you look at the periodic table. It's in the 4th column. Remember, when I say 4th column, I'm only counting the main groups or the main columns of the periodic table. I'm not counting the transition metal columns. H has 1, but there's 4 of them. And so that totals out to 8 valence electrons. So that was step 1. Step 2 is to pick the odd element in the compound or the least electronegative element and put that in the center, and then make single bonds to everything around it. So in this case, we've got 4 single bonds to the 4 H's. Then you count up the electrons that you've used up so far. So here is my 2 tricks. The first one is, once you have counted up the valence electrons here, completely forget about where they came from, okay? It's kind of like COVID right now. These valence electrons in the molecule are thinking, we're all in this together, okay? And doesn't matter where they came from, doesn't matter if they came from carbons or hydrogens. Right now, these valence electrons are involved in molecular orbitals, so that's your first hint. Don't try to plan ahead and get into your head and think, oh, well, there's 4 electrons coming from C, so it must have 4 bonds. No, just follow the system. The electrons are all in this together. Doesn't matter where they came from. The second tip is, I don't do any subtractions when I make my Lewis structures. Some people like to add up the valence electrons, then subtract out the electrons that went into bonds and use the rest to put into non-bonding pairs, but I just count up from 0. So in this case, in CH4, I know I have to get to 8 total electrons, and I know that each bond is 2 electrons. So I just count. Let me show you with a different color my counting. Okay, so I just count 1, 2, 3, 4, 5, 6, 7, 8. And there I have, I now have placed my 8 electrons. So that was step 3, which is to count the electrons placed in the bonds in the initial skeletal structure and place the remaining electrons. In this case, it was very easy because there were no remaining electrons to place. So I'll write that down, place electrons. Place electrons, the ones that are left over after you've put in the bonds. Step 4 then is to check, is everybody happy? And that means to look at your Lewis structure and make sure that everybody has a completed octet, except for the elements that are exceptions. So does carbon have a completed octet? it actually does, because you can see that it's got 1, 2, 3, 4, 5, 6, 7, 8. It's got 8 electrons around it. And so it's happy. What about the hydrogens? The hydrogens all have just 2 electrons around them. And you can see that they all have 2 electrons, and they're happy too, because hydrogen is one of the exceptions. Hydrogen is happy with 2 electrons. So that was step 4, checking for happiness. Step 5 would be, if somebody wasn't happy, then we would make some double bonds, and I'll show you that in another compound. All right, so now let's try something a little more complicated. Okay, so we're going to try CF2S. I go to the periodic table and count up all the valence electrons that these atoms are bringing to the molecule. So carbon is bringing 4. Fluorine is bringing 7 because it's a halogen. It's in the 7th column of the periodic table, but there's 2 of them. So 2 times 7 equals 14. And sulfur is bringing 6 because it's in the 6th column of the periodic table. So we have a total of 24 electrons. 24 electrons who are going to participate in the molecular orbitals and the orbitals of this compound. Remember, they don't care where they came from anymore. We don't care. We are all in this together. So step 2, put the least electronegative in the middle, which is carbon, and attach all the other atoms to it around it. F, make that F better, sulfur. Okay, so I don't know what's happening. I'm not planning ahead. I'm just following the steps. So step 3, add the others. So far I've put in, let me get a different color here. I've put in 1, 2, 3, 4, 5, 6 electrons. And so I'm just going to keep counting. As I keep counting, let me get another color. I'm going to not do any subtraction. So I'm at 6. And I'm going to place the electrons 1 atom at a time. Don't spread them out one like you're dealing cards. Just fill up, make one atom, one of the outer atoms happy, then the next atom, outer atom happy, and then the next outer atom happy. So we are at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Now I've placed all the electrons, and now so I place the electrons, check. Now I'm going to check and see if everybody's happy. And I'm going to get another color, and I'm going to check. Well, this sulfur here is happy. It's got 8 electrons around it, so it's got a completed octet. This fluorine is happy as well, and this fluorine is happy. So who's not happy? Obviously, it's carbon. Okay, so carbon only has 6 electrons around it. It's not happy. So we're going to have to do something. And what we're going to do is we're going to take 2 electrons from any atom we want, but we can take it from sulfur. We'll take these 2 electrons and put them into a double bond. And then we'll look again. So we've got carbon, fluorine, 1, 2, 3, 4, 5, 6. Fluorine again, 1, 2, 3, 4, 5, 6. And sulfur, 1, 2, 3, 4, and a double bond here. Now, we haven't gained or lost any electrons. We've still put the 24 in the molecule, but now everybody's happy, including carbon, which now has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. So it is also happy. Okay, that was our step 5, making double bonds or triple bonds where we need to so that everybody is happy. Okay, now let's look at one more thing about CF2S. I could have, if I had wanted to, I could have brought in a double bond, could have brought that electron pair in to make a double bond from a fluorine instead of a sulfur. So why didn't I? Let's look at that. Okay, so let's look at carbon double bonded to sulfur and carbon single bonded to fluorine, or carbon single bonded to sulfur, double bonded to fluorine, and single bonded to fluorine. And remember that we had non-bonding electron pairs around there and non-bonding electron pairs here. Now, let's look at the formal charges on this, because one of them is going to have better formal charges than the other. We're going to add them all up. The one that has the biggest formal charges is the worst or least stable molecule. So carbon came in with 4 electrons, and it has 1, 2, 3, 4 bonds around it. So 4 minus 4 equals 0. That's a good number. This fluorine came in with 7, and it has 1, 2, 3, 4, 5, 6, 7 around it, because you only count one. You only count 1 electron for each bond, and then 1 electron for each non-bonding electron. And that fluorine is the same. And then sulfur came in with 6, minus 2 for the bonds, minus 4 for the non-bonding electrons, makes it 0. So the total formal charges is 0. So that's a pretty darn stable molecule. Let's check this one over here. Carbon's the same. Came in with 4 valence electrons, minus the number 4 because of the 4 bonds equals 0. Let's look at this fluorine. Came in with 7, minus 6 minus 1. That's how I should have written this one as well. It's easier to see. Minus 6 minus 1 equals 0. How about this fluorine over here? Fluorine came in with 7, minus 2 for the bonds, minus 4 for the non-bonding electrons, equals 1. And this sulfur here came in with 6, minus 1 for the bonding electrons, and minus 1, 2, 3, 4, 5, 6 for the non-bonding electrons, equals minus 1, which we're going to make into an absolute value. So when we add up the absolute value of all those numbers, we get formal charges equal to 2. And that is not as stable. It's unstable. It's an unstable molecule. See, that's an unstable molecule. So that's why this is the choice. This would be the correct answer for the Lewis structure for that compound. Let's now look at the molecular geometry and the electron geometry of this molecule. And we've got carbon, double bonded to sulfur, single bonded to fluorine, single bonded to fluorine. And now I can put in the electrons if you like, but we're going to look now at the geometry of the central atoms. Well, if you caught my mistake, it's that I put extra lone pair electrons around sulfur. So let's fix that. This is the interesting thing too. When you're thinking about electron geometry and molecular geometry, you're thinking about electron groups around a central atom. Okay, so what is an electron group? Well, an electron group could be a single bond. That's an electron group. There's electron density in there. Happens to be made up of 2 electrons, but they call it an electron group. A double bond is also an electron group. That happens to be made up of 4 electrons, but it's one electron group. Another possibility for an electron group would be a triple bond or a non-bonding electron or a non-bonding electron pairs. For example, ammonia is bonded to 3 hydrogen, the nitrogen is bonded to 3 hydrogens, and then there's this non-bonding electron pair, and that's also called an electron group. So any one of those things is an electron group. Now, the main deal here is you got to think about pirates. Pirates are going to tell you what your molecular, that's a patch, geometry is, and your electron geometry. So why pirates? Well, pirates hate each other. They want to stay as far away from each other as they can. So for example, in this molecule, we have 3 electron groups around the central atom. And the only way, or the way for the electron groups to get as far away from each other as they can is in a triangular planar system. Now, each of these electron groups is 120 degrees away from each other. There's no other way that they could do that. It just doesn't happen. You couldn't, for example, make 2 like this and 1 sticking up straight, then the 1 sticking up straight would be at 90 degrees to the 2 in the plane of this screen, and 90 degrees is less than 120. So it turns out that the best way to get these electron groups far away from each other is trigonal planar. And for each molecule that you look at, that's what you kind of ask yourself. You figure out what is the best way for these electron groups to get far away from each other. In the case of ammonia, for example, this NH3 over here, this nitrogen has 4 electron groups around it. 1, 2, 3, 4. And so what's the easiest way, or the only way for the 4 electron groups to get as far apart from each other as they can? That's when they do the tetrahedral thing. So if you imagine 4 balloons, somebody's holding them very carefully in the middle, one will be coming up and one will be coming off to one side of the tetrahedron, and that's going to the back there. And then these are coming out in the front. And so they have a tetrahedral structure, and that's how the electron density gets as far away from each other as it can, each of the electron groups. The other 2 famous ones are, of course, linear, for like example, carbon dioxide. It's double bonded to 2 oxygens, and so this electron group here and this electron group here, how far away can they get? Well, the best would be 180, and that's what they do. They get 180 degrees away from each other, and it's straight up linear. So that was the electron geometry. Electron geometry is when you look at all the electron groups, the bonds as well as the non-bonding pairs, the non-bonding electrons. When you talk about molecular geometry, you look just at the bonding pair. So let me get a new layer going on here. So let's look again at ammonia. That one's going to the back, that one's coming out to the front, and then up here is an electron group. Electron pair, non-bonding pair. 4 groups, and they're all in a tetrahedral shape. But for the molecular geometry, you forget about basically the electrons, the non-bonding electrons. And you just look at the atoms in the molecule. So what shape do the atoms themselves make? Well, because they're the bottom piece of a tetrahedron, they make this thing called a trigonal pyramidal. So that's the molecular geometry. When you include the non-bonding pairs and get a tetrahedron, that would be the electron geometry. So the electron geometry equals tetrahedron. But the molecular geometry equals trigonal pyramidal. Okay, I'm going to try one more. It's HCO2 minus, just as an example. HCO2 minus. And your worksheet specifies in this case that carbon is the central atom. Let's count up the valence electrons. H is going to give me 1. Carbon is going to give me 4. The 2 oxygens are each going to give me, the 2 oxygens are each going to give me 6 times 2 is 12. And then the negative sign is going to give me another 1. because it's an ion. It's not neutral, it has an extra electron. So we have 12, 13, 14, 18 valence electrons. So we'll put the carbon in the middle, the H and the O and the O. You know, I'm not planning ahead on anything. I'm not planning ahead on where the electrons go. I'm not planning ahead on the geometry. I'm just figuring out the Lewis structure. So I have placed 3 bonds, which means I've placed 6 electrons. So I'm just going to keep counting up to 18, starting with the outer atoms. And hydrogen, I'm not going to put any on because she already has 2 electrons in that bond. So here we go. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, everybody, all the electrons have been placed. Who's happy? Who's not happy? The oxygens are happy because they have 8 around them. Hydrogen is happy because he or she has 2 around her. That oxygen is also happy. But what about carbon? Carbon is not so happy, so we'll give it a pink. Carbon only has 6 electrons around it. So we're going to take 2 electrons from either one of the oxygens and bring it into a double bond. So then we'll redraw it. This oxygen is double bonded. This oxygen is single bonded. And this hydrogen is single bonded. All right, now that we have the correct Lewis structure, and I'm just going to insert this in here. Remember, this is an ion, so we need to bracket it once we finish drawing the Lewis structure and give it its charge. Now we can think about other things. And one thing we'll notice is this actually has a resonance structure. I happen to pick the oxygen on the right to make the double bond. I could have picked the oxygen on the left to make the double bond. So it could have been this. It could have been single over here. And double over here. So this has 2 resonance structures, and usually you would draw them next to each other and draw a little double arrow, meaning that the electrons jump between one and the other, the resonance structures, basically instantaneously. So you never know which one the atom is in at any moment. Remember, again, that these are ions, and so they need their brackets. There's one, there's the other one, kind of off the screen. As you can see, I'm a learner too. So let's talk about the electron geometry and the molecular geometry of this ion. So we have carbon bonded to hydrogen, double bonded to oxygen, single bonded to oxygen. And remember that this is an ion, so we're going to put the brackets in and the charge. And how many electron groups does the central atom have around it? It has 1, 2, 3. So once more, it is trigonal planar. Well, I hope this has helped. See you next time. Bye-bye.